Hi, I'm here today to talk about DNS Distress. Okay, introduction. I'm a third-year ethical hacker. My Twitter tag's at Oren Benshabat, and I often go to cons and that kind of stuff. I like to get involved in the Infosec community. Okay, what we covered. First of all, I'm going to go into how DNS servers work, just as an introduction. I'll then talk about DNS cache poisoning. I'll then go and explain DNS amplification. Okay, what is DNS cache poisoning? DNS cache poisoning is essentially a man-in-the-middle attack against the recursive name server in order to poison its cache, so it's feeding malicious records which are false to the end user. Okay, how a DNS server works? Well, there's two. Well, everyone here is no one is. It's not really possible for someone to not use a DNS server. Anytime you request it, I want to go to google.com. You've requested it for a DNS server. It'll go out to the internet. It'll find your IP address and it'll return it to you and take you to the website. There's two main types of DNS server. You have your recursive name server or caching name server. That's the name server which you talk to directly. That's when which you ask, oh, what's the IP address for this? And it will go out to the internet to find that IP address. The other one is the authoritative DNS server. You don't talk to that one directly. The caching name server does. This is the one that's authoritative. It's in charge of an entire domain and holds all the IP addresses for that domain. Okay, and what you want to get back from one of these name servers is a DNS record. So that's what you're requesting, that's what you expect back. That's what contains the IP address from the name server. Okay, so let's step through your standard DNS request. Okay, first of all, you have your user PC going, oh, what's the IP for google.com? It sends a request up to the root servers, says, oh, no, I'm not authoritative for that, I'll refer you to the next server. And goes to the next one, goes, oh, I'm not authoritative for that, but I think I know who it might be. Send along the line, it keeps going along the line until it finds one that does, and goes, yes, I'm authoritative for that. Here's the IP address, and it sends it back to the recursive name server, which then stores it in its cache. So it doesn't need to keep going out through this process each time it wants to get the IP address. It then sends a non-authoritative answer back to the user PC, which means it's not directly from the authoritative name servers, it's from the cache. Okay, and here you have your standard DNS packet. As you see here, that's requesting for google.com, and there's the return IP address. The capital A, that means it's requesting an IP address record. Yeah, so that goes into the packets. Here's the query one. This is the one where it's actually asking, oh, what's the name for google.com? Type A, post address, and it's, as you see, it hasn't gone through any recursive name servers yet, because it hasn't no way back. On the second here, this is the first part of the response. As you can see, it's gone through several recursive name servers that's listed at the bottom, and it's got an answer, which will be on this next slide. Yeah, here you see it's gone through a bunch of Google's name servers until it finds the correct one, which has the IP address it's wanted, and that's then providing it to you. Okay, now let's look into the attack. Okay, so we have a scenario here. We have Bob who's wanting to go to google.com, log into his personal details and, I don't know, look at private things. So you have Alice who, of course, wants to carry out a phishing attack by redirecting him to a copy of Google. So what we have here is you have going, oh, how do I reach google.com? So it's asking the DNS server, oh, what's the IP address for that? And it's going through the whole process from the root servers, going until it finds one. And it goes, oh yeah, here's the IP address. And it starts sending it back. So now there's an open query here on the caching server where it's expecting a response. So then the attacking server at the same time is spamming with responses saying, yes, here's the IP address, here's the IP address. And it's just, well, hundreds and thousands of these, to be honest, depending on how much processing power they have, trying to get all the right criteria. Once one's accepted, boom, it's stored in the cache, and then it returns for google.com, it returns the malicious IP address. And every time that victim PC is going to request that same address, will go to that same address, the google.com, it's going to get the address from the cache instead of going up to it again. So this would last quite a while. Okay, what they go through is because they're not just going to accept any packet, they go through something called payload checking, which means they need to match up several criteria. First of all, the packet needs to be expected. They're not just going to accept any DNS packet then store that in their cache. Second of all, it needs to come from the same UDP port. and it needs to come from the same domain. That can be the domain one that can be easily spoofed in the packet, and you'd be worried, well, that's easy enough to send along. Also, the most important thing, the one that takes all the processing power, is the query ID. That's one that needs to be matched up. For example, if it's sending out a query of 10, it's going to expect a query ID of 10, it's going to expect a response back with a query ID of 10. And that's why they're sending so many packets out, to try and guess that query ID. Of course, it won't be something as low as 10, it'll be something massive which you need to guess correctly. Okay, yeah, so that's been compromised. He's now, I think he's on google.com, he's on whatever, maliciouswebsite.com, and he's signing in with all his details. Okay, but we take this to the next level, and on this attack, instead of just doing it for one IP address, what if you could do that for an entire domain? Well, Dan Kaminsky, back in 2008, he had an attack which he published, which was against bind servers, which was pretty major. It was a really potent attack and made quite a large bit of the web vulnerable. Well, first, way it's carried out, I'll step through it. Is first of all, you're going to request an IP address which there's no way it's going to be found, like 123xyz.google.com. That's not, you're not going to get an IP address response from that. You're getting a response from the main server, but you're not going to get like that exact IP. Okay, so that guy client, he's sending off there. What's the IP address for that? Yeah, now you have your victim name server here, you have your victim name server here, which is sending off a request to the server saying, oh, what's that? The same thing that recursive name servers do. So it's going, yeah, refer to nameserver1.google.com. It goes, okay, do you know the IP address? And there's IP address for that. And they're saying, yeah, sure. But before that's starting to respond, what's been going on is the attacker has sent up his own authoritative name server, which is authoritative for attacker in google.com. You can make a name server authoritative for anything. It doesn't mean you have any power. I can say I'm the King of France right now, doesn't mean I'm actually the King of France. But yeah, he set himself up as authoritative for google.com. And how he's spamming all these packets, thousands and thousands, to the victim name server to try match the criteria to accept that, to answer that response. So eventually one got through, so this whole packet, so this whole section here is just completely ignored. That packet just gets dropped, it's already been given an answer. Now in the caching name server, it's now cached as name server 1, and the domain google.com, it's now cached this malicious IP address. So anytime any request is going to google.com, it's just getting responses from the attacker's malicious name server. So that's like pretty major. That's an entire domain which is just like under control there. But for example, that could be, in theory, that could be taken to the next level. You could take that to the .com servers, for example, the .net servers. Think about how many responses they get from one caching name server. So that would be pretty major. Any request comes there, it's going to your site or whatever. But that would take a lot of processing power. You need to guess the query ID, and that's changing quite rapidly on .net or .com because they get a lot of requests. Yeah, so this was, at the time, this was pretty major. Sent all the companies that had DNS servers, sent them scrambling to patch things quickly because everyone was a bit scared because everything was vulnerable. Okay, but first from countermeasures. For example, what you want to do is you want to patch. What happened right away is all the bind people, they sent out patches to everyone saying, you need to patch this right away. So there's a fix for it, just in version. So it's not like an active vulnerability anymore. So that's been fixed. You can randomize the source port. So that means adds another criteria which needs to be guessed, which takes a lot more processing power. So that makes the chance of them guessing that is a lot less. DNSSEC, which is like the go-to security module for DNS, just implementing that has features which prevent these kind of things happening, and making sure you're accepting from verified sources. So, yeah, verified sources, so you have only accepting responses from domains which have been certified from like a web of trust that they are who they say they are. Okay, now I'm going to look into DNS Amplification. Okay, so what is DNS Amplification? It's essentially a type of denial of service attack using the caching name server as like the main weapon. It's like the man in the middle and the amplification source. Now it takes advantage of several things to get like a big attack going. First of all, open recursion. because there's a lot of name servers out there which will just accept DNS requests from anyone, and they'll process in that fine. So that's, yeah, the caching name server is going to act as the main AMP source and middleman in this attack. Now ideally you want a caching name server which can support large UDP packets, because the more large it can send, the better. The more data has been received on their end, the better the denial of service it is. ADNS or extension, or zero extension, which is an extension for DNS servers, which allows you to transfer packets above 512 bytes. So then again, that adds a lot more processing on the other end. I know on DNSSEC, right before, but in this case it's being used against it because it adds security, but also adds cryptographic signatures which take a lot of processing on the other end. So you're taking advantage of something useful and turning it against someone. But the good thing is, if you have DNSSEC on a server, you have ADNS 0. You need to have one, if you have one, you need to have the other. So that's great, that works pretty well together, and you have a lot of amplification going on there. Next one is DNS data corruption. For example, let's say for example you've already got a name server compromise. You can have the zone file and you can increase that to 4,000 bytes. Use that as a resource record. So when you're requesting something, you just request this record, request this record, and you're getting a much larger packet there. And all of this is adding a lot of onto the attack, so you've got quite a lot going. Okay, source address spoofing. This is another thing which can be used. What you do is altering the packet return address. So for example, the attacker will have some botnets going there, and he's going to send a signal to them and they'll all be requesting, but instead of wanting the DNS request back to them, they're changing it so it's going back to one designated target. And this victim he's then going to receive all the requests, all the answers from this caching name server, and yeah, the denial of service will be in effect. Okay, but yeah, using all these methods, the attacks can be amplified by a factor of 70 per packet. So that's quite a lot of information to process there. Let's have a scenario here. For example, someone's just been on a forum trolling people, he's pissed off someone who just thinks they're a elite hacker, it's like, oh, I'm going to hack you, denial of service, that kind of thing. Okay, so we'll look into the actual attack. I'll step through this here. Okay, first of all, you have your attacker here. Now he's sitting there at his home and he's set up he has a botnet here, which he's got quite a few, maybe a few hundred PCs or whatever size, and he's sending a request he's getting them all to send a request to the caching name server saying, oh, what's the IP address for this? And every packet there has been spoofed, so the source address has been changed to the victim PC. So then it's going through the whole process of asking the root servers, oh, I don't know, but I'll ask this other one. So it's going through each of these .com namespace, and then it gets an answer, yeah, I'm authoritative for that. So it sends an IP address back, thinking that's all fine, normal request. These caching name servers are getting them and going, oh great, now we'll just send them all, oh, they're all sending to this person. So suddenly he's getting all these packets, which are amplified by a factor of 70. He's getting every single response, and they could request on that website a few times, and he's being completely hammered by all this, and of course services are going offline, he's losing resources for his web server or whatever, and he effectively can't do anything. But yeah, countermeasures to this. There's a couple of countermeasures I have here. First of all, close open recursion, because that can just allow anyone to connect to the name server, so that's quite a problem. You just close this, you can't have massive botnets carrying out this attack. The other one, which is a much better answer, is IP source validation. So making sure it's returning the DNS request to the person who requested. Yeah. Okay, so I think I've run through that a bit fast. But yeah. Well, has anyone got any questions? Yeah.
Just a more comment. When I did look into this with the factor of 70.
Yeah.
When I was actually looking into the metrics of how they got the 70, I couldn't find any information on it. Did you manage to find how they came up with the number?
I saw a few sources where it had odd numbers here and there, but
there wasn't actually.
Yeah, every website was citing a factor of 70, but I haven't actually enough to work on the numbers. But I'm sure I can find the sources and I'll look into that first. find that.
Another thing was, going back to the attack that you mentioned back in 2008,
Yeah.
couldn't that have been mitigated just with a wildcard DNS on the authority of DNS server? Because you were using a DNS name that didn't exist, but a wildcard would have resolved to like a default, like a CNA record. So would have that mitigated it?
Might have, yeah. Well, lots of things didn't carry out this, and because, of course, these kind of people who run these kind of services, sometimes they don't really look into that kind of stuff. They don't care about security. They'll just have whatever works for them, and so they left something unprotected, and it's vulnerable.
When you've got IP source validation for a countermeasure against a DNS amplification attack, does that not cause a lot more processing power for the DNS server to then be saying, right, I know that it's being requested from here, and I'm sending it back to somebody else, but there has to be another check in place for them to validate who it actually comes from. So does that not cause like a delay, like more milliseconds on
yeah, it would cause slightly more delay, but the delay would be on the actual recursive name server instead of on like a target. So it's just the lesser of two evils.
How long would it take victims to recover from
Which one do you have? Which one do you mean? The amplification or the amplification? I'm not sure. Depending when the attack stops, for example. We'll have to wait till the. Yeah. Once the attack stopped, we'd have to just. Sorry about that. I'm just stuttering a bit here. Yeah. Once the attack against the server died down, the denial of service wasn't going on anymore. I guess their services would, the resources would just revert back to normal. So I don't think there would take that much longer once that had been sorted out. Yeah.
So the two countermeasures you've got for DNS amplification, those two are quite difficult to implement for, say, large-scale telecommunications or ISP providers, because by default they need to allow those kind of things to work. And the servers are red-side large. The benefit companies have is they can absorb the flow of traffic. It's not ideal. But is there any other things you can think of to work as a countermeasure for, say, a large-scale provider, dealing with millions upon millions of requests? That's a problem that's kind of active in the industry at the moment. So
no, I'm not sure at the moment how that could be.
You can't put the same recursion, you have to accept
You have to, there's a problem.
And because you're anyway, you can't profit based on the source of message from the front, because it looks like it's coming through.
Future research.
One of the key is the type of DNS request that's been made. It's probably atypical, and the response is atypical of DNS requests. So you probably couldn't do it within an individual DNS server, but ISPs could probably put those requests. Easy to produce a signature for DNS amplification, registered in inside the ISP.
Yeah, I think so. I'll look into that. Yeah, I still want to do more research into this and just see how this would work with more modern attacks, and so I'm going to carry on the research of this and just maybe expand that. So, yeah.
Have you had any look at IPv6 where there's similar sort of problems are evident in that?
No, I haven't yet. I'll definitely look into that actually.
Yes. So in a large organisation, one of the things that has been done to mitigate against this is that where an organisation owns, like an ISP, owns both the DNS server and the relationships with the customers, is there actually a feedback loop between the customers and the DNS server. So if it's coming under attack by somebody with a botnet, the ISP is dynamically switching off or throttling the requests of the named customers, which is a huge mitigation against that kind of thing. But that needs end-to-end visibility of your network, and it's really quite complicated to implement on a large scale.
Any other questions? Okay, thank you.